because we are doozy worthy. So what are we going to do first? Question says, describe the discontinuities. This is an extra problem. It's not in your notes or anything. So you can put it on another sheet of paper or just look at it. I don't care. What are we going to do first if we're trying to find the discontinuities?
Factor.
Got a factor. Everything a factor. So the top factors pretty readily into
-3, -2.
Okay, good. Sometimes this 5-6 combination trips us up, but we can catch you guys. You guys got it. That's perfect. All right, what about the bottom?
Oh, she got her
That's going to be factor by grouping. So what am I going to do here?
X squared.
X squared, x minus 4, minus 1, x minus 4. So there's my common factor, so that's good. And then,
X plus 1, X minus 1.
okay, so my denominator is x minus 4, x minus 1, x plus 1. Perfect. Okay? So right now, you can see there are 3 issues. There's an issue at 4, an issue at 1, and an issue at -1. Because your denominator can never be 0. Right? So now we gotta figure out, okay, I got some discontinuities, issues, breaks in the picture. What kind are they and where are they? Well, I kind of already talked about where they were, but what kind are they? Well, what do you notice right here? That cancels. So your problem reduces to this. Right? Now, in this problem, you can clearly see you're going to have an infinite discontinuity, a vertical asymptote, a non-removable discontinuity, whatever vocabulary you want to use. You're going to have them at x equals 4 and x equals 1. Would you agree with that?
Yeah.
Because these are here to stay. So when you draw your picture or graph it on your calculator, you're going to see a definite break at these 2 places. Now, in the beginning, -1 was also an issue. And in fact, if we go back to the original problem, -1 is still an issue. -1 cannot go into the original problem. It will make a 0 down here. But -1 can go in here to the new problem. So I'm going to have a whole or a removable discontinuity where x is -1. Now how do I find the y? Plug -1 in here. It won't work up there. You'll get an undefined. Now plug it in here. So my top is going to be -7. And my bottom will be -5 times -2. Is that -7/10? There you go. Okay, got it? So whatever lack of clarity there was before, we now have clarity. Perfect. Okay, now, onward and upward with our notes. Identify, oh boy. If you haven't memorized your BFF yet, get out your BFF sheet. Because now you are going to identify the BFFs with no zeros. Now, what does that mean, no zeros? That means we do not cross the x-axis. So, without looking at your sheet, try to see how many you can think of. And I gave you a hint. I said there's 3 of them. There's 3 of them. Can you think of 3 of your curves that do not touch the x-axis? Finley?
I was going to ask if you could touch it, but not pass it.
No, can't touch it.
Oh,
Oh
my God. Reciprocal.
Josh? Reciprocal. And what I'm going to do is, for purposes here, I'm going to actually draw them so you can see. This is the reciprocal function. See how it doesn't cross the x-axis? Perfect. What else?
Cosine.
Ooh, cosine crosses a lot.
Exponential.
Exponential has an asymptote at the x-axis, remember, that's your exponential. And George,
The logistic.
the logistic function also has an asymptote here and here.
What was that?
Reciprocal, exponential, logistic. Boys and girls will need to spend some time on that. Okay, you definitely need to spend time on that. Did I see you tomorrow? Okay, the next time I see you after tomorrow, we're gonna have a quiz over the BFFs. All right, so not tomorrow, but the next time after that. And what, you need to be able to answer questions like this, but you won't have your sheet. All right, so you need to know the shapes, you need to know the names, right, and you need to know the equations. All right, so anyway, no zeros. Okay, the range is all real numbers. So if the range is all real numbers, then that means whatever your picture looks like, it shoots all the way up and all the way down. Right?
Cubing function?
Cubing function, absolutely. We already talked about that one today. There's your cubing function, all the way up, all the way down. Cindy?
Identity?
The identity, which has all the same features as this guy. Very, very similar, yep, perfect. All the way up, all the way down.
The natural.
The natural logarithm, or the logarithmic. I don't care if you say natural log or if you just say log, it's the same thing. They all look like this. Very nicely done. Does everybody understand why that's all real numbers?
Oh,
We
for
all
the range.
understand why this one isn't. Sometimes kids will say this one is all real numbers. It's not because it doesn't have a zero, right? Why can't be zero? Marin?
Why would the, natural log, why would that be all real numbers? Because it can't,
Okay, we're talking about range, Marin. That's Y's. Y's go up and down.
oh,
This goes all the way down, all the way up. Right? Now, its domain is not all real numbers, but that wasn't the question, right? All right. Decreasing on the interval from negative infinity to zero, is that right? Yeah. So it's decreasing. Now, remember, decreasing means as you draw it from left to right, and we're talking about this part of the graph, negative infinity to zero, right? So as I draw it over here, my pencil is going down. So over here only is where I'm looking, and my pencil is going down. Can you think of any that are doing that?
absolute value.
Absolute value. Whoa, look at that, guys. Does that decrease on the left? It sure does. And if that one does, what's the sister to this one? The one that operates the same way? The squaring function, yeah. These two right here, these two have a lot in common, and so do these two. All right, there's one more. What's the other one that goes down? Yeah, we already have it up here, the reciprocal function. Doesn't it look like this? Isn't it going down? On that side. Perfect. All right. Odd. Whoa, whoa, whoa. What does odd mean? Symmetry about the origin. O. Odd O. Origin. So remember, that means that what you see here, you see here. Okay? So, can you think of how many are there? 4? Can you think of 4 odd functions?
Identity.
Natural identity.
Okay, one is the identity, absolutely, absolutely. Reciprocal function, definitely across the origin, perfect. George?
The sine function.
Sine function, yep, the sine function is odd. And that's one that I would like for you to just kind of remember that. We're gonna spend so much time with our sines and cosines. Sine is odd, kind of make a mental note. Sine is odd, cosine is even.
How would that be?
That one is so tricky. If the dots, open dots were on the other side, it would be. But on, you see what I mean? So that one is definitely tricky. George, you got another one?
The cubing function?
Cubing function. I think George is an odd all-star. He's got it, right there they are. Those are the odd functions. Tess? You need to talk louder, Tess. I cannot hear you, I'm sorry.
I'm confused why those two are treated.
Why, which two?
The D or the cubic and the square.
Over here?
Yeah.
Remember, I'm drawing it left to right. Follow the curve, left to right. Which way am I going?
Oh, okay.
I know that arrow is shooting up, but when we talk about increasing and decreasing, it's left to right. Left to right. Okay?
Okay, so if a function has symmetry over the origin, doesn't that mean that like
It means you can switch or make them both negative
Oh,
and
yeah, it's
cancel
like,
each other
it's
out.
like X is
So,
2, 2.
for
It could be
example,
negative
this
2,
is an
negative
easy
2.
one. This equation is
Flip
y
both
equals
sides.
x cubed.
Which is second.
If I make them both negative,
Doesn't matter.
Yes.
doesn't that equal the same thing? Don't the negatives cancel?
okay, so it's not about shape, just like if your variables are both negative, it's still
Well, it is about shape. It's about reflecting across the origin, but this is the algebraic test for it. If you take this, okay, so this is the point 1 comma 1. This is the point negative 1 comma negative 1. This is the point 2 comma 8. This will be the point negative 2 negative 8. It has symmetry across the origin. Okay, good. Now, we're gonna do a little more function analysis. Only this time, I didn't give you an equation, and I didn't give you a picture. I just said, consider this time the absolute value function. All right. This is an easy one, but let's go through it. What does it look like? It's the V. So we gotta talk about domain range and asymptotes. To start with. All right, what about domain? What's my domain for this function?
All real numbers.
So negative infinity to infinity. We're using intervals now. So yes, it is all real numbers, but we'll write that as an interval. How about my range?
0 doing.
And I'm gonna put a bracket at 0 since I have a dot there, right?
Yeah.
Everybody okay with that? That's my range? How about asymptotes?
None.
All right, extreme uncontinuity.
You have a absolute minimum.
Okay, so look at this picture. Are there high points and low points?
yeah.
Well, there's a low point, right? So you would classify that as what?
Absolute minimum.
Absolute minimum at 0, 0.
Would you be required to say it's also a local minimum?
It would be okay to say it's a local or a relative minimum, but that alone would not be enough. You have to have the absolute in there, but if you also called it local or relative, that would be fine. Yeah. How about continuity? Would you say this thing is continuous?
Yes.
Yeah, it sure is. You can draw the whole thing without lifting your pencil. And I'm gonna go ahead and indicate that by saying on its entire domain. The whole thing is continuous. There's not a break in it anywhere. Increasing and decreasing. Okay, now, this is where, Tess, you need to pay close attention here. We're talking about increasing and decreasing. We're talking about moving from the left to the right, okay? So start at the left side of my picture. What's happening? I'm decreasing. Until I get to where? The origin? So I'm decreasing from negative infinity to 0 And then what happens? I'm increasing on the rest.
You're not supposed to include 0.
That's one of those really technical points. To me, it doesn't make any sense to include at both places, because how can it be increasing and decreasing at the same place? So then you gotta decide, okay, if I can only include it once, where am I gonna include it? I don't know. So I don't include it. The guy who wrote your book does. He put in brackets both of these. I'm not gonna quibble about that.
Okay.
I happen to think he's wrong, but I'm sure he thinks I'm wrong too. All right, symmetry, boundedness, and end behavior. Does this picture have any symmetries?
Yes.
Across the y-axis. So we'll just say y-axis symmetry, which, by the way, makes it even, right? I'm just gonna write that word in there just to remind you, y-axis symmetry is even. Cosine is even. Right, what was next? Boundedness. Now, when we do boundedness, we talk about being bounded above, bounded below, or bounded. So think of your logistic function. That one is bounded. Would you agree with me? It has both a floor and a ceiling. Very few of them are bounded. That one is. Sine and cosine are bounded. What about this one though? How can you describe this one?
Bounded below.
Bounded at
It's bounded
At
below
the origin.
at y equals 0. That's its floor. Its floor is where y is 0. It doesn't go below there. If it were also bounded above, you would say above at whatever. And then if it was below and above, you would say it was bounded. Okay? And then end behavior. You will lose points if you do not use the correct notation for your end behavior. End behaviors are limits. They're the limit as we approach infinity and as we approach negative infinity. So it's the limit of the y values as x goes all the way to the right and as x goes all the way to the left. So let's look at our picture. What do you think? As we go all the way to the left and all the way to the right, what's happening?
infinity.
We're heading off into space, right? Both of them are going to positive infinity. Oh, I just thought of an awesome quiz question. Which functions, can you think of any functions that have that end behavior?
Cubic.
Cubing, definitely the cubing function. On the right it goes up, on the left it goes down.
Identity.
Identity,
Reciprocal.
no, not with that end behavior, because what does the reciprocal function do as you head off the page? It gets closer to zero, yeah, from the top and along.
Greatest integer.
Natural logarithm can't be one because it doesn't even have this side.
The greatest integer.
What?
Greatest integer.
Greatest integer, that would be another one. That way it's going up, this way it's going down. Okay, good. All right, you got a handle on that, you think? All right, let's finish this section. Number 6. Is the greatest integer function 1 to 1? Now, we need to talk about what 1 to 1 means. What did we say a function was? So, a function might be a set of ordered pairs that looks like this. That is a function, because every x has just one y, right? What do you think 1 to 1 means? A function means every x has one y.
Every y has one x.
Ah, both. So not being 1 to 1 means The X's are only used once, and the Y's are only used once. So when we did a mapping diagram, remember when we did that, we drew the arrows? There would be just one arrow coming out of every number, and one arrow going into every number. So to be 1-to-1, you not only have to pass the vertical line test, but you also have to pass the horizontal line test. Because the vertical line test checks for repeated X's, the horizontal line test checks for repeated Y's. And if you're 1-to-1, you can't have either one. So, back to the question. Is the greatest integer function 1-to-1? Absolutely not. Because think about this bar right here. Does that pass the horizontal line test? Aren't there like 2 zillion repeated Y's in there? Yeah, so it is not, because you have repeated Y values. And 1-to-1 means nothing can repeat. Which BFFs are 1-to-1?
Natural.
Okay, so let me draw pictures of the ones you're saying, the natural logarithm.
Identity.
Okay, would everybody agree 1-to-1 there? Okay, the identity.
Square root function.
Okay, time out, I can't keep up with you here. Square root function, there it is. If the identity is, so is the cubing, right? How about exponential? 1-to-1?
What's the one on top left?
How about this?
Reciprocal. That's the natural logarithm.
That's the logarithm function. Is this from 1-to-1? Yeah. Do I have my parabola up here? Is my parabola 1-to-1?
No.
Nope. Which means my absolute value isn't either. How about my sine and cosine? No. Sine and cosine are no's. What am I missing? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 2 more. Oh, we already did greatest integer. It's not 1-to-1. And what's the other one? Oh, logistic. Logistic 1-to-1? Yes. Yes. So they're all 1-to-1 except squaring, absolute value, sine, cosine, and greatest integer. Okay? Good? All right, perfect. Perfect timing. All right, so 1.3 will be due on Friday. And boys and girls, you heard me say we're having a BFF quiz our next class after tomorrow. I'll see if I can